Okay. Now the topic is true solutions. You know, solutions are classified into three types based on particle size. Okay. See, the first one is true solutions. When the particle size is less than 1 millimicron, or the same can be given as 1 nanometer. We know that 1 millimicron or 1 nanometer is nothing but 10 power minus 7 centimeter or 10 power minus 9 meter. Then coming to the second variety, colloidal solutions. In this case, the particle size is in between 1 micron to 1 millimicron. Now, what is 1 micron? Minus 4 centimeter or minus 6 meter. Then the third one is suspensions. You know, in case of suspensions, the particle size is greater than 1 micron, right? So based on particle size, we got three different types of solutions. Let me give you examples for these. See, for true solutions, let us consider sugar in water or salt in water. In this case, the particle size is the least. It will be less than 1 millimicron or 1 nanometer. Now coming to the colloidal solutions, let me give you milk as the example. Okay. Milk is nothing but liquid fat dispersed in liquid water. It's a liquid in liquid type of colloid. Now coming to suspension. Example is sand in water. Okay. Now let me tell you why did I name that chapter as true solutions. Why not solutions simply? Now let me take sugar in water. And of course, milk also. Let me take these two into consideration. You know, sugar in water appears to be homogeneous to naked eye. Even when examined using ultra microscope, it appears to be homogeneous. Whereas, if you consider milk, you know, milk appears to be homogeneous to naked eye. But when the same is examined using ultra microscope, it appears to be heterogeneous. You can see some fat particles in that. So that is the reason why I've named this as true solutions appear to be homogeneous to naked eye. Even when examined using ultra microscope also, it actually is homogeneous. Unlike milk, which appears to be homogeneous to naked eye, but when examined using a powerful or ultra microscope, it's not homogeneous, it's heterogeneous. Okay, so that is the reason why I've given the name true solutions to this chapter. We discuss about solutions like milk, nothing but colloidal solutions in a different chapter topic. I mean, under a different heading called surface chemistry. Now coming to the true solutions again. See, in this, we will have two different components. In fact, a true solution can be defined as a perfect homogeneous mixture. A perfect homogeneous mixture. Let me tell you in detail. It's called a perfect homogeneous mixture. Perfect again because unlike milk, it's homogeneous under any circumstances. Why is it called homogeneous? Say it's called homogeneous because any part or any portion of the solution will have same properties. Okay. See, a true solution is a perfect homogeneous mixture. Of two or more substances. Now, you know, these substances are called components. It's a perfect homogeneous mixture of two or more substances whose composition can be varied within certain limits. Yes, you can actually change the composition in proper limits, not of course to a greater extent, but you can change the composition. You can vary the composition within limits. So this is a true solution. A perfect homogeneous mixture of two or more substances whose composition can be varied within certain limits. Now, you know, the components of a solution are called solute and solvent. Let me give you that. You know, in general, a true solution consists of solute and solvent. Solute and solvent. Okay. Let me tell you that depending on the components, the number of components in a solution, these are of different types. You have binary solutions. A binary solution is the one that has two components. One solute, one solvent. Then there is something called ternary solution. So it consists of three components. I mean, two solutes and one solvent. Then there is a quaternary solution that has four components. Three solutes and as usual one solvent. You know, a solution can have just one solvent. Now let me tell you what actually a solute and solvent is. Now if you consider sugar in water, in general, we say that something that is dissolved is a solute and something that acts as dissolving medium is a solvent, right? Sugar is dissolved, so is a solute. Water is acting as dissolving medium, so is a solvent. But when the same is applied to, let us say, a solution consisting of liquid in liquid type Now in this case, we cannot say what is being dissolved and what is acting as dissolving medium. See, it's a liquid in liquid type of solution, right? So in this case, we can give it in two ways, depending on the percentages of these two. Suppose you got a solution consisting of 20% alcohol and 80% water. Then, you know, this is the solute and this, of course, is the solvent. Now, when you consider the same thing in, say, a different way, like 80% of this, 20% of this. In this case, this one becomes a solute and this one becomes solvent. So rather than going in, the one that is dissolved is a solute and the one that is acting as a dissolving medium as a solvent, it's better if we say that solute is something that is present in lesser proportions in a solution. The component present in lesser proportions in a solution is a solute. And the one that is present in larger or greater proportions in a solution is the solvent. Okay. Now, how to separate the solute and solvent? You know, solute and solvent cannot be separated by filtration, right? They can be separated by some physical methods like crystallization, adsorption, and distillation. We know that crystallization is a process that is based on the differences in solubilities. Of course, there are two different types: simple crystallization, fractional crystallization. We generally come across this in the qualitative analysis based on difference in solubility. In simple crystallization, you know, one will be soluble and the other one will be insoluble. Okay. Whereas in fractional crystallization, we'll be separating the things based on which is more soluble and which is less soluble. So that way we can separate the solute and solvent by crystallization. You know, adsorption of course, is a surface phenomenon. Here, one of the components gets adsorbed, whereas the other one goes off, cannot get adsorbed, based on the difference in their adsorbing tendency. Now, coming to distillation, we have different types of distillations, generally used for separating liquids from their mixture based on the difference in their boiling points. We have simple distillation, we have fractional distillation, we have vacuum distillation, and we also have steam distillation. These are the different varieties by which, of course, the solute and solvent of a solution can be separated. Crystallization, adsorption, and distillation, right? Now let us go for the classification of solutions. See, the first classification is based on the nature of a solvent. I mean, what the solvent is. You know, if the solvent is water, we say that it is aqueous solution. Now, if the solvent is other than water, that is, say, an organic solvent, in such a case, we call it a non-aqueous solution. If the solvent is alcohol, we call it alcoholic solution. And if the solvent is ether, we say ethereal solution. Okay. So this way, based on what the solvent is, we can say the type of solution. Okay. Now, the second one is on the basis of the physical state of the solvent. Right. Now, based on the physical state of the solvent, we have three types. Depending on whether the solvent is a gas or liquid or solid. See, if the solvent is a gas, we call them gaseous solutions. And if the solvent is a liquid, we call them liquid solutions. And if the solvent is a solid, we call them solid solutions. In all these cases, the solute may be a solid, a liquid, or gas. So though you got three main types of solutions on the basis of the solvent, overall you have 9 different varieties. Now let us check them out. Coming to gas in gas type, I can give you air as the example, wherein nitrogen, which is a major constituent, is considered to be the solvent. All others are treated as solutes, right? That is gas in gas type. You have different gases in air. Then coming to liquid in gas, simple, moisture or water vapor, moisture in air. Then solid in gas, we have camphor. When camphor is lighted, it goes into air, solid in gas, right? Then the second one, now gas in liquid, gas in liquid, more of gas, sorry, less of gas and more of liquid. All aerated drinks, of course, soda water. These consist of CO2 dissolved in water. Under high pressure, carbon dioxide gas is dissolved in water. Then go for liquid in liquid. Like I said, alcohol in water. Then solid in liquid. The regular ones, sugar in water or salt in water. Okay. Now coming to this one, say gas in solid. Gas in solid. We have a very important, very interesting example of occlusion of hydrogen gas on the surface of palladium. In fact, it is the adsorption of hydrogen on palladium surface. Then there is liquid in solid. We can take amalgams. Amalgams are those in which mercury is one of the components. Then go for solid in solid. All the alloys can be taken as examples for solid in solid type. For example, brass is an alloy of copper and zinc. Bronze is an alloy of copper and tin. German silver is an alloy of copper, zinc, nickel. See, there is no silver in German silver, just like no lead in lead pencil. I think you know that in lead pencil, there is graphite, there is clay, but no lead. Okay.